Now we're going to do an investigation of complex numbers. Task 1, find all values of k such that the product 3 plus 2i multiplied by 3 plus ki is a real number. So first, let's multiply 3 plus 2i by 3 plus ki. We get 9, 6i, 3ki, and then 2ki squared. And we know that 2ki squared is 2k multiplied by negative 1. So this is really just negative 2k. So we know that a complex number is a real number when b equals 0. So if we write out 9 minus 2k, this is the real part of the number, then plus 6i plus 3ki, this is the imaginary part of the number, and we want this to be 0 in order for the product to be a real number. Well, 6i plus 3ki we can factor as 6 plus 3ki, and since this has to equal 0 in order for our product to be a real number, that means we solve 6 plus 3k equals 0, and we get k equals negative 2. So that means 3 plus 2i multiplied by 3 minus 2i is a real number. And if we multiplied that out, the real number that we would get is 13. But you don't need to know that right now. So next, let's multiply a plus bi by a minus bi and see what kind of number we get. So remember, a and b are real numbers. So we're going to multiply a plus bi and a minus bi. This gives us a squared, abi, negative abi, and then this is negative b squared I squared, which is negative b squared multiplied by negative 1. So this is b squared. So this means that a plus bi multiplied by a minus bi equals a squared plus b squared. And since a and b are real numbers, that means that a squared plus b squared is a real number. And back to this example up here, we can get 13 by squaring 3 and adding it to the square of 2. This gives us 9 plus 4. And this is going to be true anytime we multiply a number of the form a plus bi by a minus bi. So if you have a complex number z of the form a plus bi, a minus bi is called the conjugate of z. we denote the conjugate of z as z bar. So it looks like a little z with a line on top. So we have a plus bi with a bar on top equaling a minus bi. So what you could say is the conjugate of a plus bi equals a minus bi. Together, a number and its conjugate are called a conjugate pair. So a plus bi and a minus bi are called a conjugate pair. The product of a complex number and its conjugate is a real number. This is what we figured out on the previous page. When we multiplied a complex number by its conjugate, we got a real number. That's what happens when we multiply 3 plus 2i by 3 minus 2i. We get the real number 13. So now let's calculate all the roots of the following polynomials to see how this plays out. So first we're going to factor out the GCF. So we get f of x equals x multiplied by x squared minus 2x plus 5. So we know that one of the zeros is 0, and to find the rest of the roots, we're going to use the quadratic formula. And we could, if we tried to test rational roots, we'd see that this quadratic has no rational roots. If we tried factoring, we would see we're not able to factor. So we use the quadratic formula to find the roots. And when we do that, we get x equals, and we use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So I plug in the coefficients I have. So this is going to be positive 2 plus or minus the square root of negative 2 squared is 4 minus 4 multiplied by 1 multiplied by 5 all over 2 multiplied by 1. Simplifying that gives 2 plus or minus the square root of 4 minus 20, so that's negative 16 all over 2. The square root of negative 16 is 4i, because 4i is the imaginary number whose square is negative 16. So I get 1 plus or minus 2i. So the roots of this polynomial function are 0, 1 plus 2i, and 1 minus 2i. I see that I have a real root and two complex roots, and the complex roots are a conjugate pair, 1 plus 2i and 1 minus 2i. I'm going to mark this as a conjugate pair. Let's do another example. So given that x minus 3 is a factor, we're going to calculate the roots of this cubic. And the hint that we're given is we should first use synthetic division to divide the coefficients of the polynomial by 3, and then use the quadratic formula. Okay, so when we use synthetic division, we get the depressed polynomial x squared plus x plus 6. Then we use the quadratic formula. So we're going to say x equals negative b, so that's negative 1, plus or minus the square root of b squared, that's 1 squared, 1, minus 4 multiplied by 1 multiplied by 6 all over 2 multiplied by 1. And that simplifies to -1 plus or minus the square root of -23 over 2. And then the square root of -23 we can rewrite as just I root 23 by factoring out the square root of -1. So we have -1 plus or minus I root 23 over 2. So the roots of this polynomial function are 3, -1 plus I root 23 over 2, and -1 minus I root 23 over 2. And we notice that we have 2 complex roots, and they are a conjugate pair. So let's write out that we notice the complex roots come in conjugate pairs.